start this session. Thanks everyone for coming. It's a much pleasure to present Dr. Luis Concha. He's an associate professor of neurobiology at the Institute of Neurobiology, Universidad Nacional Autónoma de México, Campus Juriquilla in Querétaro, Mexico. He's also the director at the National MRI Lab and lab leader of the Brain Connectivity Lab. And his lab focuses on developing imaging biomarkers of epileptogenesis in animal models, studies the cognitive impact of temporal lobe epilepsy in humans and its relationship with brain connectivity, as well as the validation of diffusion-weighted imaging to study central nervous system microstructures. It is my pleasure to welcome my friend Luis Concha.
Hello, everyone. I'd like to thank you for being here, and I want to thank also the organizing committee for inviting me. It is a great honor to have this opportunity to present my work here today with you. So we're going to be talking about epilepsy. I have nothing to declare, and I know that you know someone with epilepsy. Someone close to your life, might be your brother, a cousin, a friend, your neighbor. And that's because 1% to 2% of the population worldwide has some form of epilepsy. And 5 million new cases are diagnosed this year. Actually, I'll be willing to bet that about 24 people in this meeting have some form of epilepsy as well. So it's a very common neurological disorder. And today I am here serving as an ambassador for an amazing group of people scattered throughout the world who use neuroimaging as a tool to better understand epilepsy and advance the care of patients with epilepsy. Epilepsy is a brain disorder that causes recurring, unprovoked seizures. And a seizure is a sudden charge of abnormal electrical activity in the brain that can impact behavior. And the symptoms and the signs of the seizures depend on where in the brain this abnormal electrical activity is occurring. And as you can see from the definition in epilepsy, it has seizures, but these have to be unprovoked, and that means that not all seizures are epilepsy, but all epilepsies have seizures. If we think about the context of seizures in epilepsy, you can separate them into two major kinds. Those that have a focal onset, that means there's a part of the brain that begins this abnormal electrical activity, and those that have this abnormal activity all throughout the brain beginning roughly at the same time. The symptoms, again, depend on the section of the brain that's having these abnormalities, and they can range from motor to non-motor activities, and patients can be aware during the seizures, but often they have impaired awareness. And focal onset seizures can also progress to bilateral seizures and end up with the prototypical tonic-clonic convulsion. Of the seizure types, the focal onset are the most common, with around 60% of seizures having focal onset. And imaging has been crucial to understand the origin of these seizures and have helped diagnose patients with focal onset seizures and have allowed treatment to occur. Focal onset seizures are also the most difficult to treat pharmacologically, so identifying lesions is paramount to the treatment of these patients. There are different causes of epilepsy with focal onset seizures. The three most common ones are temporal lobe epilepsy, focal cortical dysplasia, and of course tumors. And of these three, I'll be talking about the first two: temporal lobe epilepsy, TLE, and focal cortical dysplasia. These are very common, very difficult to treat with medication, and often amenable to surgical resection that can even cure patients with these types of epilepsy. Let's begin with temporal lobe epilepsy. As its name suggests, temporal lobe epilepsy has its origin of the seizures in the temporal lobe, particularly in the mesial temporal structures. And it is often associated with a lesion that's called hippocampal sclerosis or mesial templar sclerosis that has neuronal death and gliosis of the hippocampus and adjacent mesial temporal structures. This type of epilepsy is often refractory to anti-epileptic drugs, And the hippocampal sclerosis often seen in this patient tends to be unilateral, not bilateral, but unilateral, and as shown here in this blue arrow. So back in 2003, when I was beginning my PhD at the University of Alberta with Christian Beaulieu and Donald Gross, we thought we could enhance the detection of temporal lobe epilepsy and hippocampal sclerosis by studying the white matter that is associated with the hippocampus. The hippocampus shown here in pink colors, and the fornix being its main white matter tract associated with the hippocampus, having all the output of the hippocampus to the mammillary bodies of the hypothalamus, and also carrying hippocampal afferents from the septal region. And we believed that by studying this region, we would enhance the detection of hippocampal sclerosis, and this being a bilateral structure, it would pinpoint or highlight the site of the origin of the seizures. And to do that, we were leveraging the then young diffusion tensor imaging technique that allows us to evaluate tissue microstructure by analyzing the three-dimensional profile of the diffusion of water that is modulated by tightly packed axons in a coherent fashion, and that when there are abnormalities of axonal membranes or myelin, this diffusion anisotropy tends to decrease, and it is an indirect way to evaluate the structural integrity of white matter. Derived from this, we also had tractography, and tractography allows us to do three-dimensional dissections of different white matter tracts. Here we can see the corpus callosum and arguably the most beautiful tract in the brain, which is the fornix here in green in the bottom right. If we look at the fornix from above, as seen in the cartoon on the left, and we color-coded based on fractional anisotropy, we see that control patients have a lot of warm colors, and they do so bilaterally. In contrast, patients with temporal lobe epilepsy with unilateral hippocampal sclerosis, highlighted by the asterisks in these 4 exemplary patients, you can see a lot of decreases of fractional anisotropy, which corresponds to a decrease in structural integrity of the fornix, as shown in the simplified cartoon a couple of slides ago. Now, what is interesting and was completely unexpected and against our hypothesis is that when we were expecting decreased fractional anisotropy on the fornix directly associated with the site of hippocampal sclerosis, we saw bilateral and symmetrically reduced fractional anisotropy, that meaning even on the side without hippocampal sclerosis, these fornices were abnormal. 1 year later, roughly, many of these patients had been operated on. And as expected, the fornix ipsilateral to the resection showed further reductions of fractional anisotropy because of the axonal degeneration stemming from the surgical resection. But the contralateral side did not improve. So that means that whatever was going on in the white matter of these patients did not improve upon seizure freedom. In an effort to better understand what it is that we see in this reductions of fractional anisotropy, we performed preoperative tractography and DTI in the patients that were scheduled to go resections of the temporal lobe and the hippocampus. As you can see in grayscale is the preoperative imaging and tractography, and what you see in color is the intraoperative microscope view of the surgeon. I am indebted to Dr. Matt Wheatley for allowing me to be so heavily involved in this during his surgeries. And we were able to obtain a small sample of the fimbria fornix of the patients that were undergoing seizures, temporal lobe resections, and study them under the electron microscope. Preoperative tractography with reductions of fractional anisotropy corresponded very well with overall reductions of axonal integrity, axonal density, and myelin alterations. And in those patients that had higher values of fractional anisotropy, this corresponded to densely packed, nicely organized axons. And this correlated quantitatively Specifically, the amount of membranes and the organization of these membranes within the fornix corresponded or positively correlated with fractional anisotropy. So here now we had ground truth proof that DTI can indeed talk about tissue microstructure at this level. So even though we're using a macroscopic measurement, we are able to query the underlying tissue microstructure at the mesoscopic level. Then we realized that it wasn't just the fornix that had these abnormalities. Indeed, pretty much all of the white matter tracts associated with the temporal lobe, the uncinate fasciculus, the arcuate fasciculus, and the inferior longitudinal fasciculus, in several different articles and demonstrations, it was shown that these white matter tracts have reductions of fractional anisotropy, very much like we saw in the fornix, and also in a bilateral fashion, even in patients with unilateral temporal lobe sclerosis. Even beyond the temporal lobe, the corpus callosum, the external and internal capsules, all have reductions in fractional anisotropy in both hemispheres, even in patients, again, with unilateral TLE. This was further cemented in a recent mega-analysis from the Enigma Epilepsy Consortium that included more than 1,200 patients overall. And if we just look at left temporal lobe epilepsy with over 300 patients, all the areas that you see in different colors and different shades of blue are areas that have reductions of fractional anisotropy. These, again, are patients with left TLE, and yet you can see bilateral involvement of these abnormalities. Comparing to another form of epilepsy, the prototypical genetic generalized epilepsy, that is the other type of seizures that begin throughout the brain, it's not focal, we also see that there is some damage to the white matter, also bilateral, but it is by no means as profound, as severe, and as widely distributed as what we see in patients with TLE. In a recent paper from the University of Alberta, where I did my PhD, they followed a cohort of patients and controls with temporal lobe epilepsy. They didn't follow, this was a cross-sectional study, but yet they showed that the normal trajectories of fractional anisotropy decline that you see as a function of age also occurs in patients with temporal lobe epilepsy, and to the same extent. But what is interesting here is that the intercepts of these two lines are incredibly different, and you can see that even patients with young age and young age at seizure onset already have these reductions of fractional anisotropy as compared to controls. So this argues in favor that this is a predisposing condition, and this is not something that develops over time over the course of the disease. What they saw in the body of the corpus callosum was replicated for the majority of the white matter bundles throughout the brain, very similar to the slide I showed before. Now, it's not just white matter that is altered throughout the brain in patients with temporal lobe epilepsy. A lot of work has come from many different labs. Here I'd like to highlight the work from Sarah Lariviere and Boris Bernhard and group from the MNI that showed time and time again there are reductions of the cortical thickness of the neocortex throughout the brain in patients with unilateral TLE. Also, there are volume reductions in subcortical structures, obviously the most important one being the hippocampus, because that is one of the hallmarks of hippocampal sclerosis, volume loss. But what was not recognized until not so long ago is this widespread reductions of cortical thickness throughout the brain, bilaterally again. Again, comparing to the prototypical generalized epilepsies, we see that that type of epilepsy has more reductions of volume in the subcortical structures, but not so much cortical thinning in the neocortex of these patients. So there is something particular about temporal lobe epilepsy that makes it amenable to having all these changes throughout the brain. So if we're seeing all these distributed cortical abnormalities and the alterations of the white matter pathways that are crucial for the spread of information between different gray matter regions, it is very easy to think that cognitive impairments should be related to these two things. That is because most of the cognitive functions in the brain rely on the concerted action of distributed gray matter networks. Here, and as an example, is the network, the frontoparietal network that is responsible for keeping working memory, which time and time again has been shown to be altered in patients with temporal lobe epilepsy, even though this is frontoparietal and has nothing to do with the temporal lobe. However, not all patients with temporal lobe epilepsy have the same degree of cognitive impairment. A few years ago, the group from Bruce Herman recognized that there are 3 different cognitive phenotypes in patients with temporal lobe epilepsy. So if we have on the x-axis different cognitive domains, such as language, perception, immediate memory, etc., there are some patients, roughly 50% of the patients, that will have no impairment in either of those cognitive spheres. There are, on the other hand, patients that have cognitive impairment throughout all cognitive domains. This is about a quarter of the patients with temporal lobe epilepsy. And the remainder patients will have cognitive deficits, but only in these cognitive spheres related to memory. So these can be cognitive phenotypes. They call them cluster 1, 2, and 3. We prefer the term that they coined as cognitive phenotypes. So we were wondering if cognitive phenotypes were related to the abnormal spread of information looking from a connectome perspective. So Raul Rodriguez Cruces, who was a PhD student in my lab and then joined Dr. Bernhardt's lab at the MNI, performed connectivity analysis using constrained spherical deconvolution in SIFT and derived these connectomes from which he queried different metrics at the node level about node centrality, clustering coefficient, and what I will show most is path length, which is inversely proportional to the efficiency of information flow within these networks. And Raul was able to demonstrate in these Mexican patients that the 3 different cognitive phenotypes are reproducible. We can see the same thing. Each line in these 3 plots represents a patient, and on the x-axis is one of these different cognitive domains. The gray area shows the area of normality corresponding to controls, and this is all normalized by age and years of education. And you can see that there are several patients that have no cognitive disabilities, some patients that have profound, widespread, or in different forms of cognitive domains, they have these deficits, and patients that only have memory deficits. So if we separate the patients according to these cognitive phenotypes, Raul was able to show that the characteristic path length, meaning the number of steps that information has to travel from one place to the other, the number of steps it has to go through, is considerably increased as a function of cognitive phenotype, and it is mostly increased in patients with class 3 or the 3rd cognitive phenotype in these patients, showing that there is an incredible reduction of network efficiency in patients with TLE, and that these are correlated with the degree of cognitive disabilities. And another group also showed in this summary statistic that overall network efficiency is correlated, or is a function of the degree of cognitive disabilities, again, with patients having generalized cognitive impairments showing the most decreases of network efficiency compared to those patients that don't have as marked cognitive deficits. It is not just the deep white matter structures that have abnormalities in patients with TLE. The superficial white matter is also heavily abnormal, and it also keeps this arrangement with respect to cognitive disabilities, with patients having language and memory impairment, showing the most widespread superficial white matter reductions of fractional anisotropy and increases in mean diffusivity. And if you compare that with patients that only have language impairment or patients that only have memory impairment, you see that there is a gradient of abnormalities of diffusion of superficial white matter and corresponds to what we see in network efficiency. The nice thing about having these networks fully characterized, at least at the extent that the technique allows, is that you can now play with these networks. So in a relatively recent article, it was shown that you can use these structural connectivity networks and try to simulate what the information flow is like in the brain. As beginning from an initial perturbation, which will be illustrated for this particular node, but this was repeated all throughout the brain. You perturb the initial load, and over time, you see how long it takes to reach other regions in the brain, color-coded here from blue to red. So red meaning that it took a long time for information to reach this particular node. And as a summary, we see that information reaches the frontal lobe very quickly, and that is solely dependent on the architecture of the structural connectivity. And information takes a very long time in controls to reach the temporal lobe. If we compare controls to patients, we see that there is a very dramatic increase of the speed. Information takes a very long time to reach several areas of the brain, all throughout the brain. And if you control for hippocampal sclerosis, most of these effects are gone, highlighting the very important effect that the hippocampus serves, the very important function that it serves as the hub for information distribution throughout the brain. And again, these slow information spreads were correlated with a lot of cognitive deficits in patients with TLE, replicating what we showed with the structural connectivity analysis that I showed you a couple of slides ago. Moving on into more patient-specific analysis, connectomes, structural connectomes have been used to try to predict memory impairment as a consequence of the disease and also as a consequence of surgical resection. So here are shown for illustrative purposes the different connections in the brain that are most important to predict whether these patients will have cognitive or memory decline as temporal lobe epilepsy evolves. And most importantly, you can also use these connectomes to try to predict whether a patient will be seizure-free or not after surgery. So in surgeries, either the hippocampus and amygdala are taken out selectively, or the entire temporal lobe, or a big part of the temporal lobe is resected. And it is very common a question whether this particular intervention will be useful for this particular patient. And having these connectome-based predictions, it is starting to help with the selection of patients that will mostly benefit from this very invasive but very promising procedure. I will not talk much about functional MRI because this is a diffusion talk mostly, but it is impossible to steer away from the fact that function needs to follow structure. In a recent work from the lab from Alfonso Fajardo, he showed that resting state fMRI is different in patients and controls, in patients with temporal lobe epilepsy. And there are reductions of the functional connectivity within the default mode network, and also a reduction of functional connectivity within the task-positive networks. But what's interesting is that there is increased connectivity in the interaction between these two networks. Now, normally, these two networks should be anti-correlated. That is, when there is a task being carried on by the subject, there should be increased functional connectivity in the task-positive network and a reduction of connectivity with the nodes with the default mode network. And this is not occurring in patients with temporal lobe epilepsy. They retain a high degree of synchrony between these two networks that should be completely segregated. And this is what we believe is playing a very important role in reducing cognitive abilities in patients with TLE. If we look at individual connections, say, for example, between the ipsilateral hippocampus and precentral gyrus. We look at the connectivity on the x-axis and the normalized scores for working memory on the y-axis. We see that there is a negative correlation between the two, highlighting what I just said in the past slide. And this actually occurs for many different parts of the brain. Here, every edge is showing you a significant interaction between the degree of connectivity of these two regions and some specific cognitive domain on the x-axis. So brown shows you positive correlations and green shows you negative correlations. And as you can see, there is a very distributed network of, a very distributed number and locations of these edges and connections between the brain that are tightly correlated with cognitive abilities. I've been looking at the images on the sides of the screens all week, and it reminds me of connectomes, so you probably have that too. Anyway, what causes these white matter abnormalities? The short answer is we don't know. However, they seem to be present even in children with temporal lobe epilepsy, so they are there from the get-go. They seem to progress over time, although there's some debate to that. They are related to specific histopathological substrates, as I showed with the electron microscopy slides, and they may be modulated by pharmacological treatment because drugs are known to also affect white matter structure. So a few years ago, a group from Australia advanced this hypothesis or this idea showing that some initial insult can damage the gray matter and also the adjacent white matter structures, and that over time, the repeated focal seizures can cause further damage to the white matter, and you add to that global insults based on the systemic effects of anti-seizure medication, and then you have this widespread abnormalities of the brain. This is a very interesting idea, but there are crucial areas that lack confirmation whether or not this is true, and I think there's still a lot to learn about white matter connectivity throughout the brain. Now, epilepsy and seizures are classically known to be a gray matter disorder. To be honest, it was sort of awkward to be using diffusion to look at white matter in patients with temporal lobe epilepsy. It turned out to be a can of worms or a box of Pandora, however you want to see it, to realize that the white matter in patients with TLE was so widely affected all throughout the brain. And the other reason why diffusion was not heavily used for the study of epilepsy is that gray matter is probably not the best way to use diffusion in. That is until a few years ago, where new techniques started coming out, as I will show you, that allowed us for a better characterization of the gray matter microstructure. And looking at gray matter is crucial to better understand, diagnose, and follow up patients with cryptogenic epilepsy. Cryptogenic epilepsy is, a patient has cryptogenic epilepsy when you know there is a lesion. It has to be a lesion. The seizures are focal onset, but yet you cannot find it on conventional imaging and whatever other modalities you have. So these are very tough cases because the semiology and maybe the electrophysiology points to a specific part of the brain, and yet you can pinpoint a particular lesion that is causing it. If you were to find a lesion, and it is in a place that is amenable to surgery, these patients can have a very high degree of success following resection of the lesion. So it is crucial for our community to come up with ways to better diagnose, better visualize the subtle lesions that cause cryptogenic epilepsy and get rid of that name, cryptogenic epilepsy, and just show that there is a lesion. And again, one of the most common causes of focal onset seizures is focal cortical dysplasia, which I will now highlight. Focal cortical dysplasia is an abnormality of the cortical development in which the normal layering of neurons and fibers that you have in this 6-layer prototypical neocortex is all deranged. Basically, there's no more layering, and the myeloarchitecture of this tissue is abnormal. As its name suggests, it is focal. It can occur in many different areas of the brain, and they are often refractory to pharmacological treatment. Sometimes these lesions are big, easy to find on conventional imaging, and sometimes they're not. When they are easy to see, you probably spotted them by now. They are characterized by blurring of the gray-white matter boundary. They have cortical thickness, and sometimes, not always, they'll have a hyperintense cortex, particularly on FLAIR T2. When you can see them, they're easy, but when you can't, it's really hard, unless you have an arrow pointing to them. Now, this is a real headache for clinicians around the world to try to better visualize these very subtle lesions and try to find and guide the eyes of the observer to realize, just as this arrow did, that there is indeed a lesion here, that it is amenable to surgical treatment, and this patient has a high chance of being seizure-free after resection. When you can't find it, offering surgery to patients becomes a very difficult problem. Because of this, there have been several methods advanced to try to better visualize and make extremely visible what is normally a very subtle lesion. And these methods have, for the most part, been based on conventional imaging. So you can do texture analysis. We were talking about blurring of the great white matter interface, so texture analysis lends itself to this problem quite well. You can do morphometric analysis, which has been done with good success. Machine learning methods. You can go to higher fields to try to visualize extremely subtle blurring of the great white matter junction. To all of this, you can add surface-based methods. There's a big project going on known as the MELD project, in which a large group of data has been pulled together to train machine learning algorithms and artificial intelligence to try to find these lesions. Now, what these all have in common is that they still rely on the morphological features that we've been talking about: blurring, increases of cortical thickness, and hyperintensity. This, again, can be quite subtle, and we believe that since focal cortical dysplasias are, in fact, a microscopic abnormality, diffusion is ideal to evaluate this. So this is where diffusion comes back into this talk. If we look at the prototypical neocortex, it will have a specific arrangement of neurons in different layers, and there will also be a specific lamination of myeloarchitecture with fibers going into and out of the cortex in a perpendicular fashion, and also tangential fibers that run within the cortex. The specific organization of these neurons and myelinated fibers is what gives rise to the different parts of the brain that we know as Brodmann areas and other classifications of the different cortices that you may see in textbooks. This is what gives rise to them. In FCD, again, this is all deranged. So we believe that if you are to use diffusion carefully, you can plan to see specific patterns of diffusion that is modulated by the myeloarchitecture of the brain. Now, diffusion on its own is typically not very sensitive to the organization of neurons, but it is incredibly modulated by myeloarchitecture. And in normal cortex, this is very prototypical with this organization that you can see here. However, as you can already see, diffusion tensor model will not be enough to disentangle the crossing fibers that you can see from the fibers that are going into and out of the cortex from those that are interconnecting adjacent columns in the brain. So DTI is insufficient for this task, but fortunately there have been many new methods that have been advanced in the past few years that are better tailored to tackle this problem. So there have been efforts in the community to use advanced diffusion models, such as NODI and B-tensor encoding, to try to highlight different abnormalities of focal cortical dysplasias. They are still hard, they are still difficult to visualize. These have been proofs of concepts in which the known dysplasia is known in advance, and they correspond to specific diffusion abnormalities based on these diffusion models and biophysical models that have been advanced. But we believe that it is time for diffusion to really take a deep dive into FCDs, to focal cortical dysplasias, and try to understand what are the aspects, microstructurally speaking, that can cause derangement of diffusion, and then use that diffusion to better understand where FCDs are in patients. So to do that, we turned into an animal model of focal cortical dysplasia. This is a rat animal model in which the entire cortex is diffusely deranged in terms of its myeloarchitecture. And we used 7T scanning to get high-resolution imaging of the cortex, spanning between 7 and 10 voxels across the cortex. And not only that, we used different modalities for diffusion analysis. Here I'm showing you in particular a multi-tensor approach. So that is, instead of having just one tensor trying to explain diffusion, we can fit 1, 2, or 3 different tensors within each voxel. And each of these tensors can have its own orientation and its own shape, and therefore its own fractional anisotropy. And then we separate these tensors according to how they are related to a synthetic microcolumn that we build from the white matter outgoing into the PL surface of the brain. So as you can see here in purple, we see a tensor that is, we're going to call parallel tensor, that will have fractional anisotropy parallel, that is different from the fractional anisotropy that belongs to the tensor that is tangential to the PL surface. With several rats and group analysis, we were able to show that this multi-tensor approach can show abnormalities of fractional anisotropy parallel and perpendicular in different parts of the brain, of the cortex of these rats, with FA parallel showing the most interesting or more obvious changes throughout the neocortex. MD parallel did not show that many changes as MD perp did, and they did so in different parts of the brain. And that is because different parts of the brain will have different cyto and, most importantly, myeloarchitecture that will drive or modulate the diffusion of these areas. This was a transversal studies, but if you're interested, Paulina Villaseñor now has a new longitudinal study in this same animal model that you can see in poster 2138 today and tomorrow. And more recently, we have used even more advanced models of diffusion to better understand the complexity of what's going on within a voxel inside the neocortex of these rats. And to investigate this kind of complexity, you need to use advanced acquisition methods, such as free diffusion gradient waveforms that we try to query diffusion based on its orientation and shape. Olympia Ortega will be showing her work tomorrow orally, and there's also a poster presentation. And using Q-space trajectory imaging, which tries to relate all this complexity into statistical metrics, Olympia showed that microscopic fractional anisotropy is deranged, reduced, particularly in several parts of the brain in these animals with focal corticals, or what looks like focal cortical dysplasia. And different forms of kurtosis, such as anisotropic and isotropic kurtosis, will also have decreases and increases respectively as compared to control. So for more details, make sure you visit Olympia and her presentation tomorrow. So we believe that for a complex structure, such as the neocortex, complex or more advanced methods of diffusions are needed in order to understand what really is going on there. So in conclusion, diffusion, MRI, and tractography have changed how we understand epilepsy and continue to do so. In particular, we now know, understand, and are at peace with that epilepsy, even though it may have a focal onset in the gray matter, is in fact a network disorder that involves all the white matter, for the most part, and it involves all of the cortical structures all throughout the brain. CLE, in particular, has widespread white matter abnormalities that are beyond what you see in other forms of epilepsy. They are indicative of reduced network efficiency. They are related to cognitive deficits. As you can see, this can also be harnessed to have predictive value, such as post-surgery outcome, the cognitive decline that these patients will have, and whether or not they will be responsive to treatment. What is still a big unknown is if these abnormalities are a cause or a consequence of epilepsy itself. And this is a difficult question to answer, because following patients and having patients come into the scanner before the onset of symptoms is very difficult, and we believe this is where animal models come to play a big role. And we also believe that because imaging sits at the center between the preclinical work and the clinical assessments, it serves as a fantastic tool to make these translational studies that will allow us to jump from one species to the other almost effortlessly, because diffusion tools are available in both species. Now, talking about gray matter, we know that advanced diffusion MRI can characterize gray matter, which was not possible only a few years ago. And it promises to be a fantastic tool for the better detection of subtle lesions, such as focal cortical dysplasia. And this will allow us to make the invisible visible, and for once and for all, try to get rid of the term cryptogenic epilepsies for these patients, so that doctors can offer better treatments tailored for the specific etiologies of their epilepsy. So I'd like to finish this and thank my colleagues and friends, starting from the time I was raised as a researcher during my PhD and postdoc at the University of Alberta and the MNI. I have a lot of colleagues to thank. I have a lot of students who I have presented some of their work here today. The Enigma Epilepsy Consortium has been fundamental for the advancement as a community. And I want to thank you for listening. Thank you very much.
Thanks so much, Luis. That was a great talk and just a lovely demonstration of how you can take observations from clinical populations and push them up into treatment and investigate them further in animal models. It's just lovely. And the first question agrees. It starts with beautiful work, exclamation point.
Thank you.
Especially predicting surgical outcomes. Can you map out how this can be implemented in clinical pipelines?
Okay. I have to say in advance that that is not my work. As I said, I'm serving as an ambassador of the community. Leo Bonilla has beautiful work, and other groups as well, showing the promise of these individualized medicine based on connectomes. I am not aware whether there's a tool now to bring this to the bedside table and try to make predictions on a patient-by-patient basis. What I've seen is that these replicate throughout different cohorts. So I believe that this is only a few years away from widespread use.
Thank you. So the next question is, what are white matter properties of epilepsy patients for which seizure occurrence is entirely suppressed by drugs?
Let me see if I understand whether or not patients that are controlled will have white matter abnormalities. The answer is very likely yes, they will have white matter abnormalities. There's a gray area there. They may not have as profound and as widespread reductions of fractional isotropy as we saw, but even in children with epilepsy and those that are controlled will have or will show abnormalities of white matter.
I think the next question is a really interesting one, because it's always a question in almost every disorder, is that you showed a significant number of imaging biomarkers that would be relevant to patient outcomes and the current status of patients, which I think is really interesting. How much do you think those outperform other clinical characteristics, such as, if you're thinking of outcomes and predicting outcomes and treatment courses, like, the simple things like age, epilepsy onset, seizure frequency, etc. So do you think, the imaging biomarkers are better than the things we know how to measure quite easily?
Okay. So whether or not imaging biomarkers provide even more information than what you can get in the clinic regarding outcome from surgery, etc. Yes, there have been 2 or 3 different groups that have shown the added value of imaging biomarkers. I wouldn't say they outperform, but they add a lot. If you just look at clinical metrics and put that into different classifiers, say for memory impairment or outcome after surgery, these clinical metrics are not enough to have the sensitivity and specificity to make these predictions. If you add imaging biomarkers, specifically connectome biomarkers, then you can have a lot of added value. And I think these metrics are becoming so commonplace, easy to obtain, that it will be a matter of time when they get into the clinic and help clinicians better inform their patients to understand whether or not they should have surgery or other surgical or other treatments.
So maybe a quick follow-up on that is, it's related to the next question, is that do you think the biomarkers are going to be, some of the, I guess, structure-specific measures you showed, or do you think it's going to be related to the connectome and our ability to define the connectome kind of within subject or within group or subtype to get to that stage?
I like that question a lot because I've been frustrated for 20 years that DTI and tractography have not made it into the clinic directly. Like, you cannot say the FA of the fornix in this patient is blah, 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 and therefore the patient has this other thing. You need to combine the information. And I think this comes from the fact that, as I showed, epilepsy is not a site-specific disorder. Even TLE is not a site-specific disorder. You have to take into consideration the load of abnormalities distributed throughout the brain in order to make this useful.
Okay, there we have another question. What is the proportion of MR-negative patients among your participants? Could you please elaborate on that?
Well, it depends on the group studying. In the patients that I have been studying, I try to so in patients with TLE, we get mostly MRI-positive patients. But overall, around 36% of the patients in cohorts of patients with epilepsy with suspected focal onset seizures will have MRI-negative scans. That means MRI-negative means that on conventional T1, T2, and FLAIR, read by a radiologist or neuroradiologist, these scans were read as normal. Now, if you give these scans to people with vast experience with neuroimaging, and they have all the clinical information on their right hand, they will be able to identify a lot of lesions even on these MRI-negative scans. So as I showed you before, structural abnormalities, as subtle as they are often there. So the goal is to have better techniques to make them shine, to put the eye of the observer on top of these lesions, and to then make a better diagnosis.
Yeah, I'm not sure what's going on in the background there, so I apologize. But can you maybe talk a little bit about how you can integrate what you showed today with other? Typically EEG has been one of the workhorses in epilepsy research. What is your idea of combining maybe these most sophisticated biomarkers with things that clinicians may already know, EEG, but then also maybe things that are slightly more sophisticated like MEG or PET or so on? Can you maybe... Oh, sorry. Yes. The question was, how would you combine these measures with other measures like MEG or PET to do the work that you mentioned today?
Yeah. Epilepsy is beautiful because of its interdisciplinary nature. So if you were to look at a patient and try to evaluate a patient, you never look at anything in isolation. You start from the clinic, semiology, you look at the EEG, you look at neuropsychology, you look at imaging, you look at everything and pool all that data together to make an informed decision on these patients. So the short answer is everything. Everything adds when you're dealing with patients with temporal lobe epilepsy, particularly those that have had a very hard time to be properly diagnosed. Now, keep in mind that many of the patients with hard-to-treat epilepsy take years, if not decades, to reach a tertiary care point in which all of these data can be pulled together. But when it is, the advantage to the patient is massive.
Okay, thank you. We have to finish this session, and if you have any questions, you can approach Luis directly. So thank you for coming.
Thank you very much.